In this slide, we speak about one-to-one functions. This is the first part, and we will speak about the definition, and we will give examples of one-to-one functions. In the definition, a function f from a set A to a set B is one-to-one or is an injection if whenever the value of f at x is equal to the value of f at an element y, then x is equal to y. If f is an injection, we write f is a function from A to B, and over the arrow we use these notations for one-to-one functions. The definition says that whenever you have two elements have the same image, that means these two elements are equal. In other words, we can say that different elements must have different image. Let us illustrate the definition in this example. Which of the following relations is one-to-one function? In this example, we are taking finite relations. So for number 1, f here is a function, and we see that different elements have different image, so f is one-to-one. For the second one, g also is a function, and different elements have different image, so g also is one-to-one function. The third one here, h, is not a function because we have an element which have two image, so h here is not a function, and so I cannot speak about one-to-one, the property of one-to-one. For I here, we have I is a function, but it's not one-to-one because we have a different element here have the same image, so we say that I is not one-to-one. Why? Since I of A is equal to 2 and I of D is equal to 2, but A doesn't equal to D, so it doesn't satisfy for me the condition of being one-to-one. The last one, 4 here, is also a function, but it's not one-to-one. So why? Because j of A is equal to 2 is equal to j of C, but A is not equal to C. We see that for finite functions, it's very easy to know if the function is one-to-one or not by looking to the arrow diagram of the function. Now, before we go to infinite functions, we want to use quantifiers to understand the definition of one-to-one functions. From the definition, we see that the function f from a set A to a set B is one-to-one if and only if for every x in the set A and for every y in the set A, if f of x is equal to f of y, then x is equal to y. And the fact that this means that different elements have different image comes from the contraposition. We know that this statement is supposed to be equivalent to its contraposition, and the contraposition of these statements means that for every x in A and for every y in A, if x doesn't equal to y, implies that f of x is not equal to f of y. That means different values of x in A, a difference image in B. Now we get also the definition or the conditions when the function f from A to a set B is not one-to-one function. This happens if the negation of this statement happened. That means we can find x in A and y in A such that the image of these elements are equal, but x doesn't equal to y. So to determine if a function from a set A to a set B is one-to-one, we use these conditions in the proof. So I have to assume that we have an element x and y in the set A, and we assume f of x is equal to f of y. If from this condition for arbitrary x and y, we find that x is equal to y, using this condition, we find x is equal to y, then we have a proof that f is one-to-one. Otherwise, that means we have some conditions that x doesn't equal to y, and always this will give me a counterexample why f is not one-to-one. So for our first example, we take a function s from the interval from minus infinity to 0 to the interval from minus 4 to infinity, and it is defined by the formula that the image of x is equal to x squared minus 4. We want to prove that s is one-to-one function. So I assume that x and y is in domain, and the image of x is the same as the image of y, and we want to see if this means x is equal to y. But the formula for s of x and s of y is x squared minus 4, and this one will give me y squared minus 4. So x squared minus 4 is equal to y squared minus 4. And so this will give me this equation. It gives me x squared is equal to y squared. And this gives me x is equal plus or minus y. But we know that from this condition that both x and y are non-positive, and that means x have to be equal to y. Both of them are negative numbers. Hence, s is a one-to-one function. So we see that the defining equation, the defining domain, and the defining formula for the functions lead for me x squared equal to y squared, and so we conclude that x is equal to y, and this gives me a complete proof that this function is one-to-one. So we know that if we define another function t from the intervals minus infinity to 0 to the set of all real numbers by the same formula, t of x equal x squared minus 4, as we had in the first example, then the proof of t is one-to-one will be similar to this one. That means one-to-one functions will still be one-to-one functions after we extend the codomain, because here instead of these small intervals we take all the set R, so when it extends the codomain, one-to-one functions will still remain one-to-one function. And this finished the first part about one-to-one functions.